Okay, so let's go through a worked example of a Thevenin equivalent circuit calculation. We start with the circuit that we analyzed for the Kirchhoff's laws. This has nothing to do with Thevenin initially. But what we found was we had this messy circuit here. We had a 6 volt and 9 volt battery and these three 2K resistors in a parallel combination down. We found that there's no simple way to write this just using simple resistor reduction. So we use Kirchhoff's laws. We solve for all the currents. We found that there's half a milliamp going across the 6 volt battery, 2 milliamps going across the 9 volt, and 2.5 running through this central 2K resistor. So what Thevenin's theorem tells us is that we can take this circuit and just hook wires out of A and B and use it as a battery, as a voltage source. Now, any real voltage source has some internal resistance, and that's what the Thevenin equivalent resistance is. It also has an ideal value, an ideal voltage, that's in series with that resistance, and that's called the Thevenin voltage. So let's go about solving this equation. Let's just say why we'd want to do this. Well, supposing we did do that, we had wires coming out of A and B, and we hooked something into it. Currently, we're hooking in a 2 kilo ohm resistor, and we found that there's 5 volts dropped across it and 2.5 milliamps run through it. But suppose now we want to put a 1K resistor in, or a 500 ohm resistor in, or a 10K resistor in. Each time we did this, we'd have to solve this nasty set of linear equations, do a bunch of algebra, and get a new current. So it's not super ideal. And what Thevenin is good for, one of the things that Thevenin is good for, is that if we have an unknown load, presently 2 kilo ohms, but it could be any value, we can immediately calculate the effect of plugging that load into the circuit. So let's do that. Let's start. So let's reframe this. And let's copy this over. Okay, move her around here. Bear with me as I become accustomed to this strange Microsoft software. The Thevenin problem. Instead of a resistor here, we have something. Just something we're going to plug in. It's going to be some unknown load resistor. And we don't know what it is ahead of time. Thevenin's theorem tells us that we can write this. This is always going to be equal to some battery, some ideal voltage source, V Thevenin, with a resistor in series of a given value which we calculate, R Thevenin. And here's our output nodes, A and B. And we can attach any load resistor to that and get the desired effect. So the whole idea is that this is some kind of black box with just leads sticking out of it, and we want to treat it as such, use it as a voltage source. So what is our output voltage, by the way, when we do plug in this load, when we plug anything across terminals A and B? We know this is just a voltage divider now, so we get the V out, that's what we call VAB, is just going to be equal to, from our voltage divider relation, RL over RL plus R Thevenin times V Thevenin, right? Because we have our V Thevenin ideal voltage source here and our R Thevenin. So this is what we're going to get as an output. So how do we go about getting those two values? Well, we just apply the Thevenin kind of cookbook algorithm. So step 1, we find V Thevenin. And we do that by disconnecting anything between terminal A and B. we disconnect the load resistor, and we solve for the voltage between A and B. And that's going to give us Thevenin. So now we can see how we can do this immediately. If we just take this circuit, I'll just redraw it down here. Whoopsie doodle. We have the following circuit. We have a 2K resistor, 6 volts, and then a 9 volt wedged against it, and another 2K resistor. And we're looking for the voltage between these 2 points. So for this, how do we get this voltage? Well, the easiest way to do it is just apply Kirchhoff's laws, Kirchhoff's voltage law. Now, I said the whole motivation was not doing this, but in this case, it's very simple. And that's often what you get when you're doing these Thevenin circuits. So let's just do that. Let's define a loop like this. Let's say the current is going this way. That's our loop. And we get, let's just apply it. So we're going around here. We go through the 6 volt battery backwards. So we get -6. We'll drop units again. We're going along the correct direction for resistance, for the current across the resistor. So we get -2. Again, we'll work in kilo ohms and milliamps. 2I. So I is going to be in milliamps. Minus another 2I from the second resistor here. Now we're going in the right direction for the battery. +9 equals 0. So this is what Kirchhoff's voltage rule tells us. Remember, this, the sum of the voltage drops and gains around the loop from A to B is equal to 0. Just for clarity, this is A and this is B. So this allows us to get the current. We will do so. Rewriting this, we get 3 is equal to, what's that, 2 plus 2? 4I. So I is equal to 3/4 in our units, which is 3/4 of a milliamp, 0.75 milliamps, milliamperes. Okay, so that's good. We have the current, and now we can solve for the voltage just by reapplying Kirchhoff's laws. So we're going to go around the loop. So V from A to B is equal to, again, -6 volts. We drop another 2 times 3/4. That's our across the resistor here. Equals -6 minus 1.5 equals -7.5 volts. You might say, hang on, I went around this way and I went through a 2K resistor and I got -7.5 volts. Why does that not work the other way? Well, remember that we defined the current a certain way. The current we found is flowing counterclockwise. Is that right? Counterclockwise, yes. And so, let's just say, as a note, if we decided to go in the other direction, now this is, we decided to take the other way, how would this give us a consistent result? Well, again, we'd lose 9 volts because we're going kind of against the grain of the battery, but now we're going the opposite way of the current through the resistor. So we have to add 2 times 3/4, so that gives us -9 plus 1.5 equals -7.5. So it doesn't matter which direction we go, it's consistent. The voltage drop from A to B is equal to -7.5 volts. So that's exactly what a 7.5 volt battery does. And that indeed is our Thevenin voltage. So we got V Thevenin equals 7.5 volts. And that is our first piece of our puzzle. We'll keep it. So we have the first part of our Thevenin circuit here. Great. So step 2, we're going to get our Thevenin Equivalent resistance. So our Thevenin, we simply short out, oopsie doodle, out voltages. We short out the voltages and find resistance. So let's draw our circuit. In that case, we have node A here. We just short out the 6 volt, 2 kilo ohms, another 2 kilo ohms. And luckily this equivalent resistance is easy as pie. It's a parallel combination. So our Thevenin is just, we can do it a number of ways. 1 over 2k plus 1 over 2k to the negative 1. 1/2 plus 1/2 is 1. 1 over 1 is 1 kilo ohm. 1 kilo ohm. So our Thevenin equivalent resistance now, very easily, is just 1k. So now we can fill in this black box here. Let's do that. Let's fill in the numbers. So we have 7.5 volts and 1k here. So this circuit is completely equivalent to a battery that's an ideal voltage source, 7.5 volts, and a 1k output impedance. Recall that for a good battery, it's a 1 ohm, not 1,000 ohms. This is a pretty cruddy battery, but we can still use it as a voltage source. Let's check. Let's do a sanity check here. So, let's say sanity check. Something I want to do. Oh my heavens, 1 sec. Okay. What happens if we actually just plug in our original resistor? I mean, we know what happens because we've already calculated. If we put a 2K resistor across here, we have to get 5 volts dropped and 2.5 milliamps. Let's test to make sure that that works. So RL equals 2K. We get V out equals our load resistor, 2 over 2 plus 1, that's our Thevenin voltage, times V Thevenin. And that's equal to 2/3 times 7.5 volts, which is good, I can see already, because this is 2/3. I'll just write it in a more suggestive way. That's 3/4 times 10. That's another way of writing 7.5. So we get 1/2 of 10. We got 5 volts. Big red check. So that works. That's great. And we know that there's 5 volts across. If we know there's 5 volts across 2 kilo ohms, we get 5 divided by 2k, which is 2.5 milliamps. So that works perfectly well. And we're done, pretty much. But now we can answer other questions. For example, suppose we wanted the load resistor as 1k. What does that correspond to? That's kind of messy here. What does that correspond to? Well, that's like this circuit that we originally had, except the central resistor is 1 kilo ohm instead of 2 kilo ohms. But now we can solve for it right away. What is our voltage from A to B? Now VAB is going to be equal to, that's our V out, 1k over 1 plus 1k times V Thevenin. That's 1/2 of V Thevenin. And that's going to give us 7.5 over 2, which is, if I can do math right, 3.75. I almost said 3.25. 3.75 volts. And we can have lots of fun with this. We can plug in 10k, etc. But this is the utility of the Thevenin equivalent voltage, and this is how you use it, why you use it. Because now that we've actually gone through this, we know everything about the circuit. Recall that the Thevenin voltage is the ideal case. So if we set the load resistance to infinity, V out equals V Thevenin.